Welcome to another edition of Mr. Powers Proves Something. Maybe. I hope you guys are doing well today. And today I would like to cover with you guys the come on now. Come on. Oh. This right here, the ratio test. So what is a ratio test? It's right here. If suppose we have a series, the sum of a sub n, and we find the limit of the absolute value of a sub n plus 1 over a sub n, then the if that limit is less than 1, the series is absolutely convergent. If it's greater than 1, it's divergent. If it equals 1, well then try something else. We're not sure. Anything could happen. And so we want to prove that. So how are we going to prove that? Well, let's go ahead and start with these assumptions. Let's say that we do have this L, okay? First off, and we're going to go ahead and let L be less than 1. Let L be less than 1. Okay? If L is less than 1, we're going to say there is some n there exists there is some n where if n is greater than n, so lowercase n, we're talking about here, then a sub n plus 1 over a sub n will be less than r. We can do that for sure because we're talking about a limit, right? We got this limit L. We know as we get closer and closer, as values for n get large enough, that it's going to be approaching L, and that's going to be less than r. So we know at some point we can reach these values, these large n. And well, if we know that, if we know this is true, then we would also know that just multiplying both sides by a sub n, we would have this a sub n plus 1 is less than r times the absolute value of a sub n. Now that assuming that we got this assumption here, what does that mean? Well, let's pick those values for n, shall we? Let's just say n is bigger than it. So let's start with n. So let's say here, in this case, we're going to plug in n here. If I plug in n, a sub n plus 1. Oh, I'm sorry. What am I using capital there? A sub n plus 1. If I take the absolute value of that, and we're going to go, let me see here, less than or equal to, I'm sorry, yeah, that's going to be less than r times the absolute value of a sub capital N. Okay, so we'd have that be true. Well, you know what else we'd have be true? A sub n plus 2 is going to be less than r times the absolute value a sub n plus 1. Why wouldn't that be true? That would also be true, right? And we could say, hey, a sub n plus 3 is going to be less than r times a sub n plus 2. Anyway, where am I going with this? I'm going somewhere. Oh, well, you know what's interesting is this. Almost looks like this right here, except there's an r in front. So if I was to say, take this and multiply both sides by r, this would be true, right? Because r is less than 1. Also, I know it's positive. We're taking an absolute value, a limit of an absolute value. It's positive or 0. So this value r, it's greater than L. Anyway, we know that we could multiply both sides by r. We would get r a sub n plus 1 would be less than r squared a sub n. Right there. Just multiplying both sides by r. Why not? R is a positive or 0. And we know it's not going to be 0. Is it? Would it be 0? The limit could be 0? Well, if it's 0, I guess it wouldn't matter. So we're good, right? We could do this. Well, if it's 0, I think we're in trouble, right? Because then we'd be 0 is less than 0. That wouldn't be true. So we're assuming it's not 0. All right? We're assuming that we're adding some terms here. We're not going to get 0. Okay. Well, in any case, or even if it were 0, even if L were 0, we're picking a number bigger than that. So it doesn't matter. That's right. Okay. So we multiply both sides. This would be true. This would still be true. Excuse me. Now, well, if that's the case, we could extend this. Well, wait a second. R is going to be less, so I could write, well, that's less than r squared times a sub n. Okay, great. Now, if I'm looking at this, well, this is interesting. N plus 3 is less than r times a n plus 2. Oh, so if I'm taking all of this here, maybe we try this in red. What if I took all of this and multiplied it by r? Well, then I would have an r times a sub n plus 2. I'd have an r. I'd have one of those. If I multiply both sides, all sides of this by r, we would get r a sub n plus 2 less than r squared a sub n plus 1 less than r cubed. I'm going to have to move over a little bit here. R cubed a sub n. All right. I'm starting to see a pattern here, which obviously is what we want, right? Oh, so that means I could extend this guy out here if I wanted to, this inequality, to be less than, let's see here, r squared. Oops, a sub n plus 1 less than r cubed a sub n. Now, pattern is starting to emerge. I'm starting to see a pattern here. If I'm looking at this, let's try this. If I'm looking at this guy here, and I want to compare it to something over here, which is what I want to do, that n plus 3, and then I got an r cubed, I'm thinking I could rewrite this as maybe, just in general, a sub n plus k is going to always be less than r cubed, or r to the k, sorry, times absolute value of a sub n, capital N, right there. No, I don't know. Why is that helpful? That's nice. Well, because now we can look at this series here. And because what is this? This is more or less, this is maybe our terms that we have that are greater than n, right? And then we can compare them to this series. What's this series? This series is a geometric series. Oh, yes, geometric series. I know if geometric series converges, right? When do I know of when does a geometric series converge? When r is less than 1. Well, anyway, so let's play around with this. So we're looking at this series here. From k equals 0 to infinity of a sub n, absolute value of that, times r to the k. And I know that converges when r is between 0 and 1. Do we know if r is between 0 and 1? Yes. Yes, we do. We started with that assumption. And so since we start with that assumption, we know this guy is convergent. Because what I just said, I mean, r is less than 1. It's convergent. Well, if that's convergent, then what else do we know? Well, then this guy must also be convergent too. This one. So the sum of a sub n plus k from k equals 0 to infinity. That guy's got to be convergent because it's less than the one we just said is convergent. So that's convergent by the comparison test. Yeah. So that guy is convergent. Whew. All right. Is that the hard part? Well, where can we go with now? What can we do now? Well, remember we're picking certain n's here to start with that were a certain size, right? We're kind of starting off with big n's and then going to infinity. Well, so what does that mean? Well, that means our actual sequence, which was n equals 1 to infinity of a sub n. Right? What are we talking about here? We're trying to prove if a series is convergent. So we're starting with this guy, right? We're starting with a sub n. And we want to prove if we're absolutely convergent. So in other words, this guy can be rewritten as the sum from n equals 1 to capital N of our a sub n plus this fun convergent series we just talked about, which we can rewrite as, let's say, we're going from 1 to n, and then this guy will be n plus 1. So n plus 1 to infinity of absolute value of, well, we can just say a sub n. There. So we can break up that summation this way, and we already know this is convergent. We just proved this. Just rewriting this one we have up here. So that is awesome. We got that. That's cool. Which means, what does that mean? A convergent series plus a convergent series is convergent. Now, why is this convergent? Well, because it's a finite number of terms. We're just going to n here. So that one's convergent. This part here we don't even need to worry about. The part we're going to infinity is the part we need to worry about, which we already showed converges. Oh my goodness. So that means we have proven that we're convergent if L is less than 1. Therefore, the sum n equals 1 to infinity a sub n is absolutely convergent. Absolutely convergent. When L is less than 1. That was our original assumption. Okay. Well, yeah. L being, let's go back up here, L being this guy. Okay. That's what we started with. Now, what if L is greater than 1? Now, that's the easy part. If L is greater than 1, we're going to have a totally different situation going on. Okay? So let's go ahead and say, you know what? Now let L be greater than 1. Same L as before. And so in that case now, again, let there be an n greater than or equal to some n value. And we're getting close to that limit. So we can make that same assumption, and that would be that a sub n plus 1 over a sub n, absolute value of that now, is going to be greater than 1 for some large n's. Okay? Because that's our limit. Okay. Well, in that case here, this guy would imply a sub n plus 1 is going to be greater than a sub n for some large values of n, which in its case implies that the limit as n approaches infinity of a sub n does not equal 0. What's this saying? This is saying our values are getting bigger. At some point, our terms are getting bigger and bigger and bigger, which means the limit does not equal 0. If the limit doesn't equal 0, then we have divergence by the test of divergence. So therefore, our sum, a sub n, of from n equals 1 to infinity is divergent. Excuse me. By the test for divergence. Yeah. Sure thing. Okay. Now, the last one. What if L equals 1? So we did L is less than 1. It converges. L is greater than 1. Yeah, definitely won't work. What if L equals 1? We've already seen cases where L would equal 1. And I will leave that as an exercise for you guys. Here's some examples of functions series where the ratio test will give you L equals 1. And that is 1 over n squared. Well, we got negative 1 over n. Okay, so the top one's convergent, is absolutely convergent, actually. Right, we talked about that. This guy is absolutely convergent. This is the alternating harmonic series, which we've seen is convergent, but not absolutely. So conditionally convergent. And last but not least, one that just flat out isn't convergent, our favorite non-convergent series, the harmonic series, 1 over n. We know that guy is divergent. Try it out. Stick these into the ratio test. It'll give you 1. And so in that case, you got to use some other test, right? Here, this is a convergent P series. This guy, alternating series test. And I know how to spell divergent. Divergent. And this guy, how about integral test? And there's other ways to prove that one. Okay, so divergent. And I believe that's it. That's all there is to it. So there's your proof that the ratio test is what it says it is. That it does work and it is super duper handy. With that, I bid you adieu as long as I can find this button. There we go. See you later.